Welcome back to your favorite intermediate algebra course. We're going to talk about logarithmic functions today and evaluate log functions, logarithmic functions, as well as graph some logarithmic functions. So here's your definition of a logarithm of base b, okay? Your b and your y have got to be positives, positive numbers, and your b cannot be equal to 1. And if so, then your log base b of y, and that's how you say that, log base b of y is defined as log base b of y equals x, if and only if b to the x equals y, okay? So if you have an exponential function, its inverse is the log, okay? So if you have an exponential function right there. So let's talk about real quickly, let's look at an exponential function and then its inverse, the log, and maybe you'll kind of have an idea about where this comes from. So let's say you have y equals 2 to the x, and you know what that looks like. If you pick x to be 0, 2 to the 0 is 1. If you pick x to be 1, 2 to the 1 is 2. If x to be 2, 2 squared is 4. X to be 3, 2 to the third is 8. Let's go negative 1, 2 to the negative 1 is 1 over 2 to the 1, 1 half. 2 to the negative 2 is 1 over 4, 1 over 2 squared, all right? 2 to the negative 3, 1/8, and so on, right? You got this. As this goes to negative infinity, that's a 1/8, by the way, right there. That goes to 0. Okay, so you're like, oh yeah, that's right. I know what this looks like. 2, 2, 2, 4, 3, 8, negative 1, I'm up a half. Negative 2, I'm only up a fourth, and so on. Okay. Alright, so what would, and of course you got the horizontal asymptote there. Okay, what would its inverse look like? Like, well, inverses, going to flip those x's and y's around, right? That's an inverse relation. So 1, 0, 2, 1. Instead of 2, 4, you got 4, 2. Instead of 3, 8, you got 8, 3. Instead of negative 1 1/2, you got a half, negative 1, a fourth, negative 2, and 8. Oops, negative 3. Whoops, negative 3. 8, negative 3. Let's graph that. So 1, 0, that's a very critical point right there. 1, 0. 2, 1. 4, 2. 8, 3. I got over a half, but I'm down negative 1, so about right there. A fourth of the way over, I'm at negative 2. An eighth of the way over, I'm down here at negative 3. And that horizontal asymptote at y equals 0 now becomes a vertical asymptote at x equals 0. So you got this vertical asymptote now at x equals 0. And here's your logarithm, okay? And so that's your inverse, and we call that, and this is the inverse of 2 to the x. We have this inverse log base 2 of x, okay? Okay, so we have this definition again. Let's look at it. Log base b of y equals x if and only if b to the x equals y, okay? So you have a couple logarithms that are kind of special, if you will. You have what's called the common logarithm. The common logarithm. And that's if your base is b. I'm sorry, if your base is 10. Okay? So log base 10. Okay? So that's the common log right there. Log base 10. Then you got the natural log, and this is a special one as well. And this is if your base is b. Natural log, I'm sorry, base is e. My goodness. Base is e. So if you have base e, okay, you actually call that the natural log, the ln of x, okay? This is the natural log, base e. So these two are equivalent right here. Log base e of x and the ln of x, those are the exact same thing. Okay, you can have any base as long as the base b is positive and it's not equal to 1, okay? But these are very common ones, okay? The common logarithm obviously is common, but base 10 there. And then if you have base e, the ln of x, okay? And then you have that property. Now let's see if we can run this property here. So we'll have them given in logarithmic form. logarithmic form, and we'll put it in the exponential form. Okay, so let's say you got log base 3, 81 equals 4. Then by that definition, you know 3 to the 4th equals 81. Okay, oops. 3 to the 4th equals 81. Okay, let's say you got log base 4, 1 equals 0. Then you know 4 to the 0 equals 1. 4 to the 0 equals 1. Oops. 4 to the 0 equals 1. Okay, which is true, right? Anything to the 0 power equals 1. Let's say you got log base 9 of 9. That equals 1. Then that means 9 to the 1 equals 9. So there's your exponential form for that equation there. Log base 10 of 0.01 equals negative 2. Then you would say, of course, this is a common log, right? Log base 10. 10 to the negative 2 equals 0.01. That makes sense, right? 1 over 10 squared, 1 over 100, 1/100th, that is 0.01. Okay, got this one. Log base of 4th of 4 equals negative 1. That means a 4th to the negative 1 equals 4. Okay. All right. How about this? Let's do one more. Let's say the natural log of e equals 1. Then you got to think about what is the ln of e. The ln of e is log base e, right? That's log base e is another way to write that. So you have e to the 1 equals e. Okay? So if you have a natural log, think about it that way. So that's how you can rewrite some logarithmic equations there. Now you may have noticed some of these special logarithmic values, okay? So if you have b being a positive number, such that b is not equal to 1, then anytime, write this, you have log base b, whatever b is, log base b of 1 will always equal 0. And why is that? Well, because b to whatever, to the 0 power is going to give you 1, right? So what about if you have log base b of b? What would that be equal to? Well, b to the what equals b? You know, it's got to be 1, right? Because b to the 1 equals b. Okay? Got this log base 2 of 64, and we're trying to evaluate this without a calculator here. I would, if I'm taking this, I'd set this equal to x first of all, and then I'd just run the old property, that definition. So I'd use that logarithmic form to put it in exponential form. So I say 2 to the x equals that 64. Okay, so 2 to the x equals 64. And so you got to think to yourself, well, 2 to what power gives you 64? Well, 2 times 2 is 4, times 2, 8, times 2, 16, times 2, 32, times another 2 would give you 64. So that's got to be 2 to the 6th, right? Doesn't 2 to the 6th give you 64? So in other words, x equals 6, i.e. log base 2 of 64 must be 6. Okay, because 2 to the 6th equals 64. Look at my paper here. Let's do another one. How about all right, so problem B here. Log base a half of 0.25 equals what? So I say, well, I want to find out what is, right? So now I put it in exponential form. So 1/2 to the x power equals 0.25. And let me put 0.25 as a fraction here equals a fourth. Okay, what would x have to be? Well, isn't 1/2 squared equal to 1/4, right? 1 squared over 2 squared. So x must be 2. In other words, log base 1/2 of 0.25 must be 2. Okay. Next one, how about log base 1/3 of 27? Log base 1/3 of 27. So, well, let's find out what it is. Let's set equal to x, and then let's put an exponential form. 1/3 of the x power equals 27. And then you think about this, you're like, well, 1/3 to the 1 is 1/3. 1/3 squared would be 1/9. 1/3 to the third would be 1/27. So I'm going the wrong way, right? It's getting increasingly closer to 0. So what about 1/3 to the -1? Would that work? Well, 1/3 to the -1, if you're thinking, this might be some thoughts that you're just thinking, right? That's 1 to the -1 over 3 to the -1. In other words, 3 to the 1 over 1 to the 1, right? When you run the negative exponent definition there. So you got 3. You're like, so it's not -1. How about to the -3? There you go. That's 1 to the -3. 3 to -3. So the 3 to -3, that goes up. So you simplify that. There it is. 3 times 3 times 3 is 27 all over 1. Check mark. So x must be -3. In other words, log base 1/3 of 27 is actually equal to -3. Okay. About got one more here. How about log base 4 of 2? What is that equal to? Set equal to x. Run it. 4 to the x equals 2. So 4 to what power? You say, well, isn't 4 to the 1/2 actually equal to 2? In other words, the square root of 4, isn't that 4 to the 1/2? Like, oh, yes it is. So x must be 1/2. So log base 4 of 2 equals 1/2. And that's how you solve those when you're evaluating logarithmic expressions by hand. There's a few examples there. Okay. Now there's some inverse properties. Get a new thing here. So if you are simplifying some expressions, let's do this one first. 10 to the log base 10. You know what? Let me. Okay. 10 to the log of 2.3. Now you notice that log has no base, right? So if there's no base, it's assumed to be the common log. So this is 10 to the log base 10 of 2.3. Now, 10 to the x, which looks something like that, right? And log base 10 of x, these are inverses, so they undo each other, okay? Remember, if you have inverses, they will undo each other, okay? They'll spit out x. They're reflections about the line y equals x. Okay, so if you have 10 to the log base 10 of 2.3, guess what you have? 2.3 is your answer. Okay, it also goes the other way. If you have, we'll do it this way, log base 10 of, let's go 10 to the 2.3. Guess what that is? 2.3. Let's do some other ones. How about log base 2 of 8 to the x? Now you notice the base and this base here, those are not the same, are they? So you're like, I wonder if I could force that. I need that 8 to be 2, right? Because 2 to the x and log base 2 of x, those are inverses, right? So I want them to undo each other. So I say, can I rewrite 8 as 2 to the something? Sure. Isn't 2 to the third actually 8? And it's 8 to the x, right? So now I can rewrite this so I recognize them, the composition here. Okay, so log base 2 of 2 to the 3x is 3x. They undo each other. That's an inverse property there. Okay. how about, let me do another one. Let's do the natural log of e to the 2x, okay? Now, I mentioned previously that the natural log of x is the exact same thing as log base e of x, right? It's just that they call it the ln of x, the natural log. It's special, it's log base e. So if you need to think about the ln being log base e, and then recognizing, oh, okay, they're inverses here, they undo each other, it just spits out 2x. You may want to think about that, okay? But the ln and e, they undo each other, okay? And it also goes the other way. So if you have e to the, say you got e to the ln of 17, that's just 17, okay? Because that's the same as e to the log base e of 17. So they undo each other and it spits out 17, okay? All right, let's go ahead and find some inverses now. Let's find some inverses. Yeah. All right, find the inverse. So let's say we have this, y equals log base a half of x, okay? If you guys remember when we found inverses, okay, the first thing that we would do is we would switch x and y, right? So you want to do that same thing here. Let's go ahead, switch x and y. So x equals log base a half of y, okay? And now, once you're at this point, you want to say, well, how do I solve for this y right there? Okay, so you can do a couple things. First of all, let me write this log base a half. Let me switch their sides there. There's that commutative property, okay? So at this point, you can do one of two things. You can either run the definition, so write in exponential form, 1/2 to the x power equals y, and there you have it. Y equals 1/2 to the x, which is our inverse of the original function, right? So there's our inverse. Or you can also think about, at this point, you can also say, what would undo the log base a half? And I say, well, that's if I take 1/2 to each side here. 1/2 to that, so now log base a half of y is in my exponent, and 1/2 to that. Because 1/2 to the log base half of y is just y. It undoes it. And now I got 1/2 to the x. You see how those are the same thing? Okay. We can do another one. How about find the inverse on this one? Find the inverse. Y equals the ln of x minus 2. Okay. So you say, well, I switch x and y again. Okay. And I prefer to put this ln y minus 2 over here equals x, right? Now I have to undo the ln. Okay, so who's the inverse of the natural log, right? Here's my natural log. Or in other words, log base e, right? Same thing. Who's its inverse? E to the x, right? So I undo that by going e to this side, e to that side. Because e to the ln of y minus 2 is just y minus 2. And then I solve for y. So e to the x plus 2. And that's my inverse. F inverse of x, e to the x plus 2. Okay? The other way you could have done that is right here at this point where you had the ln of y minus 2 equals x. You say, well, the ln is log base e, right? So at that point right there, I can say e to the x equals that y minus 2, and then I add 2 to both sides. So e to the x plus 2. Either of those would have worked. There's my inverse. e to the x plus 2. Okay? But remember, the natural log and e to the x, those are inverses, right? Okay, when I started this section, I introduced, talked about the 2 to the x and its inverse being log base 2 of x. So let's revisit a little bit some graphs of logarithmic functions here. Actually, let me do it right here. Okay, so some graphs. If you have, here's your general form here. Log base b x minus h plus k, okay? Now, your h is going to move you horizontally. That's your horizontal shift. Your k is going to be your vertical shift, okay? And you're going to also have a vertical asymptote. Since you're moving it right or left with that h, you're going to have a vertical asymptote at x equals h, okay? So let's think about, how about, let's first look at 3 to the x, and then we'll graph its inverse. So we really want to look at log base 3 of x, right? Okay, so we know 3 to the x, plug in 0, 3 to the 0, 1, 1, plug in 3, 3 to the 1, 3, 2, going to give us 9, negative 1 is going to give us 1/3, negative 2, 1/9, and so on. So we have this. Anyways, we're like that with our horizontal asymptote, y equals 0. Okay, now let's look at log base 3 of x. So if you want to plug some points in, okay, let's start with 1. Log base 3 of 1. Or maybe you want to think about it this way. Log base 3 of 1 equals y. So 3 to the y equals 1. Well, what would y have to be? 0. So when I plugged in 1, y must be 0, right? Which makes sense because I originally had 0, 1. Now I have 1, 0, right? 3 to the x and log base 3 of x are going to be inverses. Now let's plug in, now the next nice one to plug in is going to be where this x, right here, I want it to be 3 to the something, right? So like, let's let x be 3, if x is 3. Log base 3 of 3 to the 1 is 1. Remember, they undo each other, right? Now let's pick x to be 9, 3 squared. Isn't log base 3 of 3 squared, so I'm letting x be 9. Log base 3 of 3 squared is 2, right? So let's put those points on this graph here. I got 1, 0. I got 3, 1. I got 9, 2. Okay. So far you kind of see that spot, right? Now let's pick our, how about 3 to the negative 1? So let's go log base 3, and let's let x be 3 to the negative 1. So our x is 3 to the negative 1. Well, what's 3 to the negative 1? That's 1/3, right? And what's it spit out? Log base 3, 3 to the negative 1 is negative 1. So a third of the way to the right, I'm down at negative 1. Okay, the next one I'm going to pick is 1/9, or 3 to the negative 2. Log base 3, 3 to negative 2 is negative 2. So when I have a 9th, I'm down 2, okay, and so on. You see this thing starts shooting down. The closer I get to 0, the further this thing will shoot down, okay? So I have this vertical asymptote. So I have a vertical asymptote here at x equals 0. My domain is, let me erase some of this here. Down. Okay, my domain such that you see how it takes off from the 0 goes to the right, except we never quite touch that x value of 0. Okay, so I say my domain is x is greater than 0. You can think about the former range on that blue one, 3 to the x. The range was y greater than 0. That means our domain is going to be x greater than 0 for its inverse, right? And then finally our range now, our range. You see how this thing keeps going lower, right? And you see how as you go to the right, it keeps going steadily, steadily up, up, up. So y is going to be all real numbers. Okay? All right. And of course, you can shift that right, left, up, down. Okay? So same sort of shifts. If you had log base 3 of x minus 3, that would be right 3. So it's the same graph because it's log base 3, except it's right 3 and it's up 2. Up 2. So I would take this point right here, 1, 0, right 3, 1, 2, 3, up 2. Now it's right there, okay? And I've shifted my original vertical asymptote x equals 0. I've shifted that to the right 3, right? And everything shifts right 3 and up 2, and I could do the rest of them. Whoops, that's kind of what it looks like there. But I can do all those shifts with it, okay? So that's kind of how you take a look at graphing logarithmic functions. We'll do some of that in class, and we can ask some questions as well. See you soon.